SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustion, Module 7, Thermodynamics of Reactive Systems. So, in this module, we had 2 lectures. Now we will be discussing about the second lecture. In the first lecture, we discussed about chemical and thermal analysis of reacting systems, and in today's lecture we will be talking about the conservation equations for reacting flows. So, more or less in our last lecture we have given many reactor models in which the chemical reactions can be quantified theoretically. But when you do these theoretical computations, we also require the fundamental laws. We also expect that fundamental laws needs to be satisfied. So, in our today's discussions, we will be looking at the simplified conservation of equations for reacting flows. And in this lecture, we will talk about the conservation methods, like we have mass, energy and momentum conservations. Then we have mass conservation as well as species mass conservations, because here the conventional mass conservation differs for combustion system is that because the reactant breaks and they form products. So, there is a loss of reactants and gain in the products. So, in addition to that, there are many individual species that are formed in the process of reactions. So, those species also has the principle of satisfying the conservation equations. So, those equations we call as a species mass conservations. Then we will discuss about multi-component diffusions in a situation that when there are more number of species and during the reaction process one can diffuse others, and there is a diffusion also depends on their relative merits. At the same time, diffusion also affects the global chemical kinetics. So, the multi-component systems gives certain glimpses of those aspects. Then we have momentum and energy conservation equations. Here we will see that how the fundamental forces they balance, and in fact while talking about momentum conservation we are mainly focused on the pressure difference that happens during the reaction process. Then we have the energy conservation equations, which essentially talks about the heat balance equations. And towards the end we will give some important concept. One is conserved scalar, other is conditions of chemical equilibriums. So, we will cover as and when it appears, but before we proceed for that, let me give some emphasis that the chemical process or the chemical reaction when it takes place, there are lot of species formations, there are many reactions which we have seen that in an H2O2 model, in a methane combustions or nitrogen NOx formation, there are many equations are possible, and more or less unless and until we deal specifically as a research topics, it is very difficult to give a very overview or fundamental pictures. So, in our discussion today, we will not discuss every topic elaborately, mainly conservation equations, mainly because we are not covering the derivations and all, but rather while dealing the combustion systems, how those conservation equations differs than the conventional systems. This is the entire philosophy or importance of this lectures. Now when you deal with the multi-component reaction systems, and they are very complex both in physical as well as mathematical form, that is true also. And so they are often dealt with simple governing equations mainly in one dimensional framework. So one dimensional framework is the simplest methods. It can be two dimensional or three dimensional framework. The reactions may be infinite number of reactions, maybe hundreds of reactions, and for which we require some kind of hands-on packages to deal with all kinds of processes, reaction processes, endothermic, exothermic, species, individual species, their enthalpy balance and so on. But anyway, for our discussion in the one dimensional framework, we will talk about a simple steady flow one dimensional planar geometry. We have also a model for steady flow one dimensional spherical geometry and steady flow two dimensional axisymmetric geometry. These three concepts are very fundamentals. Why? When you say look at a planar frame, because when you deal with the combustion systems, we normally see a planar flame. Where this planar flame comes, this is basically during pre-mixed combustions. Pre-mixed combustion means in an SI engines, for a simple example. And another situation or geometry that is important, that is spherical geometric scheme. So spherical geometry scheme means like this is a situation where we have a droplet evaporation or droplet burning is burning of fuels. So to analyze such kind of energy or mass conservation equations, we use spherical flame. The last one is something like axisymmetric analysis, which is helpful, jet flame or diffusion flame. So this is axisymmetric, spherical and planar schemes. Now we will move on to planar systems, which is mainly for a pre-mixed combustion systems. What you see is that we are looking at a planar medium, and that medium which is separated by a distance delta x, in which there is some mass, that reactance that enters in a single axis, that is one dimensional axis, x axis, and some products that goes out after forming a certain reactions. So during this reaction process, there are some species that gets generated. Within this control volume, there is also change in the mass. So this is all about the mass conservations. So we expect that we have a one dimensional control volume with planar layer of fixed thickness through which the mass enters and leaves, and the rate at which the mass increases within the control volume is nothing but the difference in the mass that flows into and out of the control volume. This is the very basics of mass conservations, and we all know. Another important fact is that many conservation principle, when you deal with earlier, many times density is normally a fixed quantity, but here in the combustion system density varies within the position. So density has to be taken as a variable quantity. So accordingly, we can write the overall mass conservation equations in a vector form, like dou rho by dou t plus gradient of rho into v vector is equal to 0. This is for mass conservation. Same mass if you write for individual species, instead of rho we are writing rho times yi. Yi may be mole fractions, and rho also replaced with yi, its mole fractions. And in the velocity term, we can say that velocity vector, in addition to this we have diffusion component of species I. But here when you talk about the species conservations, there is a net production of species. So that is in the right hand side, it is not 0, it is m dot I vector triple dash, and this is nothing but the net production rate of species per unit volume. We expect that mixture mass flux is nothing but summation of all these species mass flux, and this also can be represented in terms of the mole fraction and velocity vector of the individual species. In addition to that, mixture mass flux is also can be expressed in the form of global velocity, and this we call this as a, here we introduce two terms. One is mass average bulk velocity, which is v vector, and species velocity, that is vi. So vi is your species velocities and v vector is the mass average bulk velocity, and the difference between these two is the diffusional velocity. So how it looks like, we can see here that diffusion velocities for species I is nothing but small v vector minus capital V vector, which is nothing but the difference between the species velocity and the bulk velocity. Other important aspect is that we also, in addition to the mass conservation, we also expect that there should be species conservations, and the total species mass flux can be equated as bulk mass flow flux plus diffusion mass flux. So, from these equations we can arrive at the another equations involving mole fraction of species I and velocity of the velocity vector and the diffusional component of the velocity vector for the species I. So, here a simplified assumptions that if there are only two species, one can invoke this Fick's law where the diffusion component of velocities can be expressed in the terms of binary diffusion coefficients. So, if you have two species A and B, so their species mass flux can be quantified in terms of two terms, one is the bulk mass flux, other is nothing but the diffusional components of species mass flux. So, this is how the mass and species conservation equation looks like. Then we will move on to multi-component systems. So, let us try to see that what a multi-component system is all about and why we need to have a multi-component analysis. In the modeling and understanding of detailed combustion systems, particularly laminar, premixed and non-premixed flame, the concept of binary diffusion is not a right representation, because binary diffusion is among two species. But in a combustion system there are maybe many number of species and there may be interrelated coefficients, and also the species can behave in a different manner in a mixture. So, instead of binary diffusion coefficients, we can write it as a effective diffusion coefficients. So, a more appropriate when there are multiple number of species. In fact, there are large number of species present in the mixtures and the properties of individual species may be greatly different. For example, heavy molecules may diffuse less rapidly in the lightweight atoms, that is true, and many times there may be large pressure gradient in the flames, which may be the driving force for the mass transfer in addition to concentration gradient, because Fick's law only talks about concentration gradient, but it does not talk about any information about thermal gradients or temperature gradients. So, this may be another driving force in a multi-component diffusion systems. And this temperature gradient effect diffusion term during the mass diffusion is commonly referred as thermal diffusions, and many times we call this as a Soret effect in conversion terminology. So, diffusion process that arises due to the temperature gradient is known as the Soret effect. Other aspect is that the thermal diffusions also results the light molecules diffusing from low to high temperature regions, and conversely heavy molecule diffuse from high to low temperature regions. So, light molecules go up and heavy molecules come down. So, that means this is how the diffusion process looks like. But in these discussions we will talk about some of the basic preliminary concepts of multi-component systems and how they need to be attempted. So, basically when you talk about the species in a multi-component mixtures, there are four distinct modes of mass diffusions. One is ordinary diffusions, and that results from the concentration gradients, and if there is only ordinary diffusion, then we can use the Fick's law to quantify this mass diffusion. But in addition to that, if there are temperature gradients, then we may have thermal or Soret diffusion. There are also the diffusion that results due to gradient in the pressures, so we call this as a pressure diffusions. There are possibilities of unequal body force among the species, so these are called force diffusions. So, out of these four, the first two terms are most important in the conventional combustion systems, and the pressure diffusion terms takes over is normally not too large to be taken into account in counter of with respect to ordinary or thermal diffusions. And but force diffusion term will come only when in a reaction instead of species, if these species are in the form of ions. So, when I say ions, obviously it is a positive or negative charged particles. For example, a chemical reaction that takes place in an electrical environment. So, we expect there may be formation of ions. So, when such a thing happens, then the reaction as to the unbalanced body force needs to be taken into account, and such diffusion process we will call it as a force diffusion. So, in general, when you talk about add all these terms, we can define diffusion mass flux and diffusion velocities, and these velocities are nothing but the combinations of all these components, which is can be expressed in the vectorical form. And also each term, and in particular if you neglect this pressure term and force terms, then there are two important terms, diffusion flux due to concentration gradient and mass and velocity diffusion due to the concentration gradient, and mass and velocity component due to the temperature gradient. And in particular they can be expressed in the form of mixture pressure, temperatures, molecular weight of the species, and with summation of all these species. So, here if you look at this term, the term that is going to be introduced here is Dij, which is effective diffusion coefficients, and that arises due to this concentration gradient. Similarly, due to this concentration gradient, we have the velocity component of diffusion species. But while talking about the thermal components, we have a term DIT which arises thermal diffusion coefficients. But however, in our preliminary study, we will only focus on the diffusion components due to concentration only. So, to do that, one simplest analysis that can be made, or it can be considered as an approximate methods, is a multi-component mixtures with species diffusion flux and velocity equations to be represented in the form of binary diffusion coefficients, and for which we can recall Fick's law. So, basically what we are trying to find out, that we need to evaluate this effective binary diffusion coefficient for species I in the mixture M in a simplified manner, and the sum of all the species of diffusion coefficient is set to 0 to obtain the diffusion velocity of n species. This is as per the Fick's law. Now, when you do that, we can write these two terms, mainly diffusion mass flux and diffusion velocities. So, here we write, instead of Ij we write Im. I stands for species, M is with respect to mixture. So, the mixture may have many species. So, accordingly we have mole fractions Yi and gradient of these mole fractions. So, this is how we write these equations for diffusion mass flux and diffusion velocity. By setting the sum of species diffusion flux to be 0, we can find out another expressions like diffusion velocities for n species, and for all these equations the binary diffusion coefficients with respect to mixture is defined in this manner: Dim, I stands for species, M stands for mixture. So, it is 1 minus concentration of Xi, here I stands for the species, and J can be other components in the mixture. So, J is not equal to 1, but it starts from second, third and fourth onwards. Then we will move to, just for a continuity sake, we will just briefly discuss about the momentum and energy conservation equations. If you write the entire equations of energy and momentum, then it will be a huge task, and for this course it is almost beyond the scope. So, what I have written is that I have written two simple equations. What says is that momentum equations, which says that pressure is constant throughout the flow field. That means, unless and until there is a pressure gradient exists during reactions, and the reaction process is something like independent of pressure. Other thing is that we are writing one dimensional energy equations in this particular form, which says that the sum of rate of sensible enthalpy transport by convection per unit volume plus the rate of sensible enthalpy transport by diffusion per unit volume. So, this sum is equal to rate of sensible enthalpy productions by the chemical reaction per unit volume. So, this is the general expressions that are used here, and here the term that are frequently important is thermal conductivity K, rho is the density, Cp is the specific heat, D is the diffusion coefficient, and all these properties are regarded as transport properties. And one of the form of this one dimensional equations is Sabhab-Geldovi's energy equations, which is written in the integral forms. So, more details we can go through the fundamental books. We are not going to discuss further on this aspect. The most important aspect of this lecture is to define quantities which are regarded as conserved scalar. Okay. So, normally we have two quantities, scalar quantity and vector quantities, but conserved scalar comes as a word, that means any scalar quantity which remains conserved during the reaction process. So, if you look at reaction globally, normally reactants vanishes, products are formed, but what we can see is that when the reactant vanishes, there is some origin of certain fuel component that have traces throughout the reaction process. And if you want to calculate a particular information about that species, then that conserved scalar is a one of the good approach, and two such important conserved scalars are absolute enthalpy and mixture fractions. So, in a combustion reaction there are many such conserved scalar are possible, but only absolute enthalpy and mixture fractions are very important conserved scalar. And in fact, where this conserved scalar concept is important, this is mainly when we have non-premixed flame. When you have non-premixed flame means fuel or oxidizer species, they come separately, but when they come separately not necessarily it forms an homogeneous mixture. So, it is a heterogeneous kind of mixture, but whereas in a premixed situation it is a homogeneous mixture, and of course, the conserved scalar has does not provide any extra informations, because we already have mass fractions, mole fractions, all these terms, and this conserved scalar will also fall in the similar line, but where it becomes important, because when there is a non-premixed flames, that means fuel and oxidizer streams are comes separately. So, with this viewpoint we say that in the combustion framework absolute enthalpy and mixture fractions qualifies as important conserved scalar. Why absolute enthalpy is conserved? Because it is conserved in every point during the flow where there is no sources of thermal energy. Absolute enthalpy remains constant everywhere because there is no source of thermal energy. Also enthalpy can change, but absolute enthalpy cannot change, that is throughout the process we represent. Element mass fractions are conserved scalar. Element mass fraction conserved scalar because the elements are neither created or nor destroyed by the chemical reactions, because either fuel or oxidizer stream, if you have a fuel and oxidizer, both comes and after reactions they form another species. So, that means the species are neither created nor destroyed during the chemical reaction. Another important aspect is that the conserved scalar is a very particularly useful in dealing with diffusion flames where fuel and oxidizer streams are initially segregated. But however, in pre-mixed combustion situations, the conserved mixture fraction does not provide any new information. Now, let us see how you want to calculate the mixture fraction F, and which is typically considered as a conserved scalar. So, for which we take a flow systems that consist of single inlet stream of pure fuel together with single stream of pure oxidizers. And when you do that, what we see is that 1 kg of fuel, when it mixes with mu kg of oxidizer, it gives mu plus 1 kg of products. Of course, prior to this we defined mass fractions, mole fractions of fuel and oxidizer of each species, but this conserved scalar definition it says that this mixture fraction F is equal to mass of material originating from the fuel streams. For example, in hydrocarbon fuels, the mass of the materials are carbon and hydrogen. So, the presence of total mass of carbon and hydrogen in the mixture divided by the mass of the mixtures. So, the mass of the mixtures can consist of fuel stream species, oxidizer stream species and so on. So, what we can say that this number F, when you calculate in a oxidizer stream, this number is 0. When you calculate in a fuel stream, this number is 1, and during the flow field or during the combustion process, this value can take any number between 0 to 1. So, in a 3 species systems, we can define F in terms of fuel and oxidizers and the product mass fraction in the flow fields. So, for these reactions, when you say 1 kg of fuel plus mu kg of oxidizer gives mu kg of products, mu plus 1 kg of products, then the mixture fraction F can be defined as YF into 1, that is in the fuel it is 1, and for products it is 1 by mu plus 1, and for oxidizer it is 0. So, total if you simplify these equations, so you can find out F is equal to YF plus 1 by mu plus 1 into Y products, where YF stands for kg of fuel per kg of mixture, Y products stands for kg products per kg mixture, Y oxidizer is kg oxidizer per kg mixture. And after saying so, the last component of discussion in this module is the conditions for chemical equilibrium. So, we all these times we have talked about the total thermodynamic equilibrium consists of 0 unbalanced force, no change in the temperatures, the system is in thermal equilibrium, system is in mechanical equilibrium. Another part segment is that the system should be in chemical equilibrium. Now, to satisfy the conditions of chemical equilibrium, we recall a simple hydrostatic systems of constant mass, which may be homogeneous or exogenous. They are in mechanical as well as thermal equilibrium, but not in chemical equilibrium. And when they are not in chemical equilibriums, so we expect that there has to be some irreversible process that is going on due to chemical reactions, and this irreversible change can be defined as the entropy productions, which involves chemical reaction due to the chemical reactions, and the entropy change for the reservoir. That means, when the reaction is in contact with a reservoir, so we can say the change in the entropy for the reservoir. So, for that things we can find out the total change in the universe is ds 0 plus ds is greater than 0, that is law of entropy. We can write this ds by 0 is equal to minus dq by t, and when you put it here we write this expression minus dq by t plus ds is greater than 0, and this gives an equations dq minus tds is less than 0. Now, if you recall the first law of thermodynamics, we say dq is equal to du plus dw, or it becomes pdv. So, we write this equation in the form now du plus pdv minus tds is greater than 0. So, this equation now represented in this form. Here you take a stand that when you are looking at a constant temperature and volume systems, for constant temperature and volume situations, we write these equations P dV is equal to 0, which means d of u minus Ts is less than 0, and what is this u minus Ts is nothing but Helmholtz function d xi less than 0. So, what it says is that in a constant temperature and volume system, Helmholtz functions must be less than 0. Now, in a constant temperature and pressure process, in a constant temperature and pressure process, we can rewrite this equation as d u plus Pv minus Ts is equal to 0. So, u plus Pv is nothing but H enthalpy. So, u H minus Ts is equal to 0, and H minus Ts is represented as a Gibbs functions. So, change in the Gibbs function is less than 0. So, there are two sets of thermodynamic conditions for chemical equilibrium by considering the principle of increase in the entropy. So, first one is the Helmholtz function for a system at constant T and V decreases during an irreversible process, and it becomes minimum at final equilibrium state. So, it is called as thermodynamic potential at constant volume. Another term that comes in is Gibbs function for the system at constant T and P decreases during an irreversible process and it becomes minimum at the final equilibrium state. So, Gibbs function is minimum at the final equilibrium state, Helmholtz function is minimum at final equilibrium state. So, this is called as thermodynamic potential of constant pressure when the Gibbs function becomes minimum at the final equilibrium state. So, this is all about this lecture. Now, today we will solve some numerical problems based on the understanding of our lecture. So, the first problem is about a multi-component system. The mixture contains this H2, O2 and N2, and for which their mole fractions we write xi x2 is equal to 0.16, xi O2 is equal to 0.22, xi N2 is equal to 0.68. We need to calculate the effective binary diffusion coefficients. To find this effective binary coefficients, you recall this expression DIM, which is nothing but 1 minus xi I divided by summation of j 1 to n xj divided by d I j, and here m stands for mixture. Of course, j is not equal to I. So, if I want to write these expressions for these two terms, first thing if I want to write d H2 m, here we say I as H2, j can be O2 and N2. So, we write this as 1 minus xi H2 divided by xi O2 divided by d H2 O2 plus xi N2 divided by d H2 and N2. Second case, if I write d O2 mixture, so here I is O2, j is N2 and O2, N2 and H2. So, 1 minus xi O2 divided by xi O2 divided H2 d O2 H2 plus xi N2 divided by d O2 N2. Third term we write d N2 m. So, effective binary diffusion coefficients for nitrogen. So, I write 1 minus, so here I is N2, j is O2 and H2. So, we write 1 minus xi N2 divided by xi H2 d N2 H2 plus xi O2 divided by d N2 O2. Okay. So, here the terms like dH2O2 is given, dH2N2 is given, dN2O2 is given, and we also know xi H2, O2 and N2. So, by inserting values, numerical values, we can find out effective binary diffusion coefficients d H2 m is equal to 2.27 centimeter square per second. dO2 m is equal to 0.75 centimeter square per second. dN2 m is equal to 0.84 centimeter square per second. So, this is how a simple system process tells how in a 3 component system how to calculate effective binary diffusion coefficients. So, in fact, if there are more number of species, then this summation has to be further extended. Now, the next problem is that in the same multi-component systems involving H2, O2 and N2 with certain mole fractions, and we know their mole fractions, and we have to write the expression for diffusion velocity. So, diffusion velocities can be written by 2 expressions. One is VI diffusion, and in here it is mainly with respect to concentrations. So, we write minus DIM divided by YI gradient of YI. So, YI is the concentration gradient, YI is the mole fractions, gradient of Y talks about the concentration gradient. So, if you write this for H2, so I write H2 diffusion, then we have to say minus d H2 m divided by mole fraction of H2 d y H2 divided by dx. Similarly, for O2, V O2 diffusion will be minus d O2 m divided by y O2 d y O2 divided by dx. And in fact, what is given is the mole fraction of this y H2, y O2 and y N2 is also given. Last term we can write V N2 diffusion, we write minus gradient of N2 m divided by y N2 d of y N2 divided by dx. This is one way we write the diffusion flux. There is another expressions which also can be written diffusion coefficient in the form of molecular weight, that is 1 by xi I molecular weight of mixture summation of j is equal to 1 to n molecular weight of j d I j gradient of x j. Okay. So, if you say I is equal to H2, j is equal to O2 and N2. So, this equation we can write V H2 is equal to 1 my x H2 molecular weight of mixture, then we have molecular weight of O2 d H2 O2, then dx O2 divided by dx plus molecular weight of N2 d H2 N2 into d of x N2 divided by dx. Then if you, when you say for O2, then we say I is equal to O2, j is equal to N2 H2. We write 1 by xi O2 molecular weight of mixture, then we say molecular weight of H2 d O2 H2 dx of H2 divided by dx plus molecular weight of N2 dO2 N2 d of x N2 divided by dx. Similarly, we can write B of N2. It is 1 by xi N2 molecular weight of mixture, entire bracket. We write molecular weight of H2 d of N2 H2 dx of H2 by dx plus molecular weight of, here we say I is equal to N2, J is equal to O2 H2. So, then we have to write O2. So, d N2 O2 d of x O2 divided by dx. So, this is how we can write the expression for diffusion velocities for each species, and one method we can write this way, other method we can write in this form. See, the last problem is we are talking about the conserved scalar, and which is nothing but your definition, which is the mixture fraction, and it is expressed in terms of mole fractions. So, to solve this problem, first thing that you need to understand is that what are the species. The species that are available at any instant is during a combustion process, it is C2H6, CO, CO2, H2, H2O, N2, O2 and OH. At any instant of time we find these species available. Now, if you look at the fuel stream consists of C2H6 and it consists of the compounds or materials which is carbon and hydrogen. Now, air stream, it consists of N2 and O2, and here you do not see any kind of fuel components. And flame gas, and when you talk about flame gases are this. Here what is the source of fuel stream? So, carbon is present in C2H6, second is CO, third is CO2. Hydrogen is present where? In C2H6, in H2, in H2O and in OH. So, basically while calculating F, what we write? MC plus MH in the mixture divided by M mixture. Now, let us see what is this, how do you find out this. So, this can be represented as this. So, but let us see what, first talk about carbon, then we will talk about hydrogen. So, carbon is present in these three streams C2H6, CO and CO2. So, we write in terms of their mass fraction as Y. Y stands for mass fraction, X stands for mole fractions. So, the relation between mass fraction and mole fraction is Yi is equal to Xi into molecular weight of I divided by molecular weight of mixture. So, we are writing in terms of mass fraction first. So, we write C2H6. So, when you say C2H6, 2 moles of carbon. So, we write 2is molecular weight for carbon divided by molecular weight of C2H6. First term, second term we write YCO. So, you can write molecular weight for, since there is 1 mole, so we say MWC by MWCO. Then it also CO2 it is present. So, we write Y CO2, so it contains 1 mole. So, molecular weight for carbon divided by molecular weight of CO2. Next stream we are going for hydrogens plus Y C2 H6 3 molecular weight of H2 divided by molecular weight of C2 H6. The next element is H2 itself. So, IH2 divided by molecular weight of H2 divided by molecular weight of H2. Then H2O. So, H2O molecular weight of H2 divided by molecular weight of H2O. Then OH. So, here half mole. So, IOH plus 0.5 molecular weight of H2 divided by molecular weight of H. So, by inserting the relation between mass fraction and mole fractions, so the F can be represented as twice xi C2H6 plus X CO plus X CO2, and this is molecular weight for carbon. So, this is first part of this expression. Second part is 3 xi C2H6 plus xi H2 plus xi H2O plus half xi OH. This is molecular weight for hydrogen. This divided by mixture, molecular weight of mixture. So, this mixture contains all these species. So, molecular weight of mixture I can write as summation of xi I molecular weight of species. So, xi I for H2S6, xi I for CO and so on. So, this is how we define the mixture fractions, which is basically a conserved scalar in a situation in a non-premixed ethane air flame which contains C2H6, CO, CO2, H2, H2O, N2, O2 and OH. So, this is all about module 7. With this we conclude this lecture as well as this module. Thank you for your attention.